Okay, so now we're going to talk about consumer surplus. Uh, Consumer surplus is going to be our first notion of welfare. So in this class, we're going to be interested a lot in what is the way of analyzing the value or efficiency or welfare or justice or something, equity of different particular setups of the economy. Uh, Price regimes, income regimes, ways of thinking about like allocation across different people once we get to more market-based stuff. And the first notion is just going to be this little simple thing called consumer surplus. So what we're interested in is at a given price, how well off is a consumer? And how much do they benefit from this particular set of prices? So let's think about this from a demand perspective. If we have a demand curve and we know that a consumer is buying bananas at 20p per banana, she buys 10, right? So in her demand curve, when the price is 20, she buys 10. Her demand is 10. When the price goes up to 25, she only buys 5. Okay, now we just observe these two different pieces, right? We observe this statement 1, we observe statement 2. These are things that are maybe empirically verifiable. You could go to a store and look at the demands. You could calculate it from the while-raising demands. But the point is that we see that her consumption drops when the price goes up, a downward sloping demand curve, great. Now, what does that mean? When she's buying the when she's buying the bananas for 20p. When she's buying the bananas for only 20, she buys 10, but we know that the first 5 bananas were worth more than 20p to her. We know that they were worth at least 25p because she was willing to buy those 5 for a more expensive price, right? So the first 5 bananas are worth more than what she ended up paying for them. And this you could think of as kind of arising from, it's related to, in some sense, this notion of decreasing marginal utility or decreasing marginal rates of substitution, thinking of what you can buy with that, the money that you're spending on the bananas. If we have this decreasing notion of marginal value, either marginal utility or marginal rates of substitution, then as you get more bananas, they're going to become worth less, right? So the first banana I'm willing to spend a lot of money on because I don't have any, and I could have used that money to buy apples or cherries or something else, and I chose to use it on bananas because I didn't have any, and so one banana is very valuable. Once I have a bunch of bananas, I become less willing to buy more, right? And this is this we can track this through all of our assumptions, but it really comes down just to the idea of a downward sloping demand curve. That as bananas become more expensive, I want less of them. So what we can do is we can actually look at this. So I guess we can start to think about how to quantify this surplus. The surplus being how much more you were willing to buy, how much more you were willing to spend to buy the amount that you ended up getting. Well, if she buys 10 bananas, we could calculate, well, how much was she willing to spend on one banana? So that's and the difference between that and the price she actually paid was like some notion of her surplus. Like she was willing to pay 30 cents for the first banana and only paid 20. The second one maybe 28 cents, the second one 25 cents, whatever. And we could see that the total amount that she's willing to pay is how much she's willing to pay for each unit that she purchases, less the amount that she actually paid. So we can take a quick look at what that looks like graphically. We have our demand curve. So this is our, whoa, snapping here. I don't want that. We have our price of good X, and we have our demand for good X on the X-axis. And it's something, it's downward sloping like this. And so what does this mean? It means that if the price, so let's say this is the first unit, right, of the good. Well, she's willing to pay this price for that unit, right? She's willing to pay this price. That's the definition of this demand curve. If she was buying one unit of the good X, she'd be willing to pay the corresponding P of X to buy that unit. But let's say that the actual price is, well, now I like the snap, it's like sometimes you need it. The actual price, this is P bar, right? This is the actual price she pays in the market. Px, this axis is calculating the price of X. The curve is the demand curve, right? So this is, we could write this X star of P. This is the value, how much he's willing to demand given a price. Obviously, the axes are flipped. I mean, it's really P of X. It's called the inverse demand curve. It doesn't really matter. The point is that this is the relationship between the quantity demanded and the price. This is the actual price that she's paying in the market. P bar is the actual price that she goes and pays. And now what's interesting is this first unit, she gets some surplus, right? So the surplus that she gets is that much surplus, right? And she bought one unit at that much, which means she gets this bar of surplus, right? The second unit, she would get this bar of surplus, blah, blah, blah. But really, we're not thinking about buying it in terms of units. We're thinking about buying infinitesimal amounts, which means we're not going to do this triangular or this rectangular approximation. It's just the entire area under this curve, right? So this entire area under this curve is how much surplus. It's measured in like units of currency or something, but it's how much surplus she gets by purchasing. Right, the actual amount that she purchases is given by this point here. That's the actual demand. And this is like the hypothetical demand had the price been more expensive. But she was willing to buy this first unit for substantially more, right? That's the difference between what she actually paid and what she's willing to pay. And for this unit, this is the difference, right? And so we're just going to integrate along that curve. So the definition of consumer surplus from a mathematical perspective, 100% not what I wanted to do. From a mathematical perspective, is just the integral under the curve, the demand curve, and above the price. So let's take a look at an example of that. The consumer has a utility x times y plus y. She has a wealth of I and faces prices px and py. And we're going to ask what is her consumer surplus when she consumes at a price I over 2. So the price of good X is half of her income, and whatever her income is divided by 2. So we can write down the Lagrangian. We're going to assume strictly positive consumption. So we're just going to ignore, we're going to assume that the first order conditions hold, and we're going to ignore the budget constraint potentially being slack. So the Lagrangian is the utility function ux plus u of xy, which is xy plus y, minus lambda, and then the budget constraint being negative, so that's pxx plus pyy minus the income. We have 3 first order conditions with respect to x, y, and I guess it should be lambda. I wrote mu1. At some point I changed the notation. So hopefully no one has any problems here. This is just simple, this is just algebraic, take the derivatives and then we're just setting them equal to 0. So we can divide px by lx by ly, right? And we get that y over x plus 1, the marginal rate of substitution between x and y, has to be equal to the ratio of prices. We can use this identity to solve for y in terms of x. So we divide both sides by, multiply both sides by x plus 1, and we get that y is equal to the ratio of prices times x plus 1. We can plug that back into our budget constraint, right? So that we get pxx plus py times this value for y, the py's cancel out, and we're left with px, x plus 1. And then we just, solve for x. And so you can solve for x by, you divide by, so you divide by px, right? So you get I divided by px, and then you'd get a, you'd have one more px, you'd have a 1. Yeah, okay, that's right. A couple of steps missing, but I wouldn't worry about it too much. You can handle that on your own, I think, some basic algebra. So we get that x star is equal to I minus px over 2y, and y is equal to I plus px over 2py. And this requires that px is less than I. Otherwise, x star would be negative, and so we'd run into a boundary condition. So if px is less than I, then these are the solutions. If px is greater than or equal to I, then x star is 0, and y is just spend all your income on y. We have a corner solution. So we found the Walrasian demands, and now we're interested in finding the consumer surplus. Well, the consumer surplus is the integral of the demand function. So the demand function is px is a function of px and I, and it's just given by the thing we just had. And now we want to integrate the area below the demand curve and above the price, right? So below the demand curve and above the price. So that's just the integral of this demand function. So if we come back, so this is just the integral of the demand function, right? And the only question is, what are the bounds of integration? Where are these bounds coming from, right? So if we take a look at the graph that we drew before, we're thinking of x as a function of p, right? We were writing the demand function as a function of p, which means we're really thinking about this as this, right? We're really thinking about this as a function with x on the x-axis, on the y-axis, and p on the x-axis. And I mean, it like frustrates me no end that this is the way economists think about this, but that's the way economists think about this, right? Is putting them on the wrong axis. But we can revert. We're just integrating along the y-axis, not the x-axis, right? We have this demand function, and so we want to integrate from this point. We want to integrate from this point What's going on? Okay, I don't know what just happened. So we want to find the value, the size of this green triangle, right? And this green triangle, what we have is a function, this function here, which is x star as a function of p, right? That's what we solved for. That was our Walrasian demand. And so if we're interested in x star as a function of p, we want to integrate underneath that curve, beneath the bounds, from here to here. Well, this bound is pretty obvious, right? That bound is just p bar. That's just or px or whatever. That is the value, that's the price of x that the consumer actually pays. And what is the boundary on the other side? Well, this is where x star hits 0, right? So this is where the demand is equal to 0. So we want to solve for where x star is equal to 0. So the upper bound, notice that this is also kind of mirrored in the sense that this is increasing p. So the upper bound of our integration is where the demand is equal to 0, and the lower bound of our integration is the actual price paid. And that makes sense, right? We're looking at all of the things that you would have bought had it, how much you would have paid for each unit had it been more expensive, had you bought less. Sorry. You want to look at how much did each thing cost had you bought this is like on the boundary of what I would redo as a video. I think I might leave it. I think I'm playing fast and loose today. So let me just restate what I just said so that we can be clear about it. We're looking for the size of this green rectangle, the green triangle. That's what lies below this function. The function is x as a function of p. It's a demand function characterized by a price, the price of x. And we know what the function is. That's just our demand function. We just need to know what our bounds of integration is. And the bounds of integration are on the lower side, the price paid, and the upper side, the price at which I would demand 0, or the consumer would demand 0. And the reason is that we're interested in each, in this case, horizontal band here, each thing here is a value, is some consumption that was demanded, but that the consumer was willing to pay more than she actually paid. And so the last place where she would have bought more and been willing to pay more is the maximum amount she's willing to pay, which is the infinitesimally first unit that you'd buy, right? So the amount that she'd be willing to pay when she has zero demand or zero consumption. So that's where x is equal to 0. So if we go back to our example, we see that x star is equal to 0 when px is equal to I. So the upper bound of our integration is I, and our lower bound was the price paid, which we said was I over 2. And so that is, and then you just integrate across that demand function, and that gives you the consumer surplus. Most of the examples we're going to do in class is with a linear demand function. So instead of starting out with a utility function, we're going to start out with the demand function as the primitive, and we're going to just assume it's linear because that makes this very easy. And then you just have to find the size of a triangle, and the size of a triangle you can find without integration. You can just find by multiplying the sides by each other and then dividing by 2, right? So yeah, that's all we got on this video. Cool. A little bit sloppy, right? But I mean, hopefully still high quality, you know, an 80% or so.